All right, so we're going to first look at longitudinal force transfer. Okay, so this is the idea that if you want to improve muscle quality and you want to get more force from the same amount of muscle, one thing that you can do is you can make the muscle structures a little bit stiffer. And so I give an example here of what happens when you have 10 kilos weight on a muscle sarcomere, but the structures within the sarcomere are stretchy. What you can see is you start contracting the muscle, and you contract the muscle, you've got your cross bridges shortening. You can see that the H zone is shortening here because we've got more overlap of the thin filament and the thick filament, but we still didn't get much movement to our weight. We pull, but it's like pulling on a rubber band. You stretch it a long way before the weight at the end of the rubber band actually starts to move. If instead you stiffen up the structures, so we show here alpha-actinin, which is the Z-line protein, that's stiffer, maybe a little bit stiffer titin, maybe a little bit of other stiffer proteins. Now, when I go and I contract my myofibers, so my myofilament proteins interact the exact same amount, the contractile proteins shorten, the sarcomere shortens the exact same amount. But now what happens is we transmit the force better, and look, we've moved the weight further. We move the weight twice as far. Okay, so the idea that if you can figure out the things that are important in longitudinal force transfer, and that's going to be things like the Z-line, so alpha-actinin and the associated proteins, and then things like titin, which is this big, huge protein that goes, it's this one right in here, it's part of the thick filament, and it's the biggest protein in your body. And so what we're going to do now is you've got these proteins, and if they're shorter varieties of them, you should be able to transmit force faster, and you should be able to develop power faster. And this is what we call the rate of force development. So rate of force development is how quickly we can move or develop force. So in the top example, we're developing force, but it's taking us longer than in the bottom one. You can see the length of the arrow is telling us we've gone twice as far as we did in the top one. So that's an increase in rate of force development. And this can be true for any of the structures in series. So it could be true for the tendon getting stiffer, the muscle getting stiffer, or the muscle extracellular matrix getting stiffer. All of those things will affect longitudinal force transfer. One of the best known examples of how this would work is the protein, the Z-line protein, alpha-actinin. And it's specifically alpha-actinin 3, which is it's going to be associated if you have this mutation that's an RR mutation. So it's a single nucleotide polymorphism where you have two R's instead of the X's. Okay, so the XX is basically one polymorphism. The RR is another. If you get two R's, one from each of your parents, you'll be an RR. If you get an R from your mom and an X from your dad, you're going to be an RX. And if you get an X from both, you're going to be an XX. Okay? So one of the things that was identified early on is that when you look at elite endurance athletes, they have more of the XX phenotype than the elite power athletes. If you want to be an elite power athlete, apparently, it seems like this XX phenotype is a little bit prohibitive because you see very, very few elite power athletes with the XX phenotype. Whereas you look in the controls, about 20% of the controls are XX. And if you look at the endurance component, you're going to see that you're enriched for endurance if you have the XX. All right? And so the idea here is that alpha-actinin is this protein that could allow you to transmit force better through the Z-line. And if it makes a stiffer sarcomere, now you can develop force faster and you can be a better power athlete. Just to give you an idea as to how important this is some work that we did at the USA Track and Field National Championships, where we took all of the different throwers that they had and all of these elite national level throwers. And what we had them do is we had them do an isometric squat, and we measured how quickly they developed force in that isometric squat. And then we looked at their performance and we made it relative to the top 5 performances in 2014. We didn't make it relative to the world record because the world record's been, let's say, marginalized by the fact that a lot of people were competing for that world record with performance-enhancing drugs. So now what we did is we've got this idea of how did you perform relative to the best in the world versus how quickly you were able to develop force in your legs. And what we see is there's a really good tight correlation. So the correlation is good. It's not a really steep correlation because you wouldn't expect us to be able to find at the elite level something that would be that if you did it a little bit, you would have a big response. But what you can see is those who developed force faster performed better relative to the rest of the world. Okay? So that gives you an idea that this is an important thing. So how hard is this to change? Well, a few of the athletes that we had in this cohort then came down and did a workout. Same thing 5 weeks later. Again, it's a smaller competition, it's not USA's, but it was trying to mimic what would happen between USA's and the World Championships or the Olympics. And so one of the athletes was Gwen Berry. She came in, and when she was in Sacramento for the USA Championships, this is her rate of force. This is her isometric force in the legs, isometric squat. And you can see that the blue line was in Sacramento. The red line was in Chula Vista, which was this period 5 weeks later. Her training had changed. You can see her rate of force development changed. So she's developing force faster in the red line than the blue line. You can see the slope is shifted over to the left a little bit. And that resulted in a small 18% change in rate of force development. But if we looked at her improvements in performance based on that, she had a 2.5% improvement, and she was a hammer thrower. So that made her go from 5th place to 1st place. Okay? So I want you to notice something here. And again, this idea of, strength is really important. Well, this is a woman who is pushing with her legs. She's producing 560 pounds of force. Okay? She's not weak. She's hella strong. She's got to throw a hammer that weighs 8.8 pounds. So if I get up to 575 pounds in strength, it's still 8.8 pounds. It's not about the weight, we don't think. It's not about the weight of the object that she's throwing. It's about being able to develop force quickly so that she can transition really quickly and get the distance on the performance. Okay, so what this is maybe suggesting is that it's not the absolute strength necessarily. Maybe it's how quickly you can develop that strength. And that's going to be determined by not only your contractile proteins, but all of these proteins that transmit the force along the muscle all the way to the tendons and to the bones. Okay, so longitudinal force transfer is the transfer of force along the length of the muscle. It's important in determining the rate of force development. And rate of force development is the best predictor that we have seen in elite power performance. If you stiffen the series elastic component, all of these little elastic bits in the muscle fibers or around the muscle fibers or in the muscle, what you're going to be able to do is you're going to be able to transmit force more quickly to the bone and produce force or produce movement more rapidly. Mutations such as the RR variant of the alpha-actinin that potentially increase stiffness in the longitudinal force transfer, improve speed, power, performance, and the result is that most of the elite power athletes have the RR form of alpha-actinin, where most of the endurance athletes maybe have fewer of the RR mutations and more of the XX form.